Okay, so welcome back to this next video in which we are discussing subgroups. Okay, so in this video what I want to do is look at another example of the subgroups of a group. Okay, so we're going to look at the subgroups of the group of integers under addition. Okay, so firstly let me just remind you of the group of integers under addition. Right, so the set then that underlies the group is just the set of all integers. Okay, so the set containing all the whole numbers 0, 1, -1, 2, -2, 3, -3, and on it goes. Okay, so that's the set of all integers. Okay, and now to turn this into a group, what we need is the composition law, and the composition law that we're going to be considering is addition. Okay, now I know that there is multiplication also defined on the integers. Okay, and that's also a composition law, but for our purposes at the moment, forget that that exists. All that I care about at the moment is the composition of addition, basically, that I can add any two integers together. Okay, right, so this is my group of integers under addition then, this set of integers with this composition law defined on it. Now let's just talk through the fact that the composition law on this set of integers actually does obey the axioms of group theory. Okay, so let's remember what the axioms of group theory are. This composition law needs to be closed, which is to say that whenever we take two integers a and b, okay, so two arbitrary integers a and b, and add them together, we must get another integer. The answer to the composition must be within our set of integers, basically. So all of the entries in this composition table must be elements of this set, basically. And hopefully that's familiar to you, that when you add two whole numbers together, you end up with another whole number. Okay, right, so closure is obeyed. Okay, second property is associativity. Hopefully this one is also intuitive to you from your understanding of classical algebra. So remember, associativity is basically saying that when we consider the composition of three things, a plus b plus c, that has one and only one answer, that it doesn't matter where we put the brackets. Okay, so you can either choose to put the brackets around a plus b, take the answer to a plus b first, and then add that answer to c, or you can choose to take a and add it to the answer of b plus c, basically, and it does not matter which way you decide to do this. A plus b plus c has one and only one answer, and hopefully that should be familiar to you from your understanding of classical algebra. Okay, so addition on the integers does obey associativity. Okay, right. Thirdly, it needs to have an identity element. There needs to be an element which will compose or add with any other element to give that arbitrary other element back again, and that's true either side, well, either way round that you compose them, basically. Okay, and of course that's 0. 0 will add to any other element of the integers to just give that other element of the integers back again. Okay, right, and finally we need it to contain inverses, so we need for any element there to be another element within this set that will compose with it, that will add with it, to give the identity 0 back again. Well, of course that's just the negative of the element. So for instance 1 has -1, which it will compose with to give the identity 0 back again. -1 has 1, which it will compose with to give the identity back again. Okay. 3 has -3, which it can compose with to give the identity 0 back again. So all the elements in here do indeed have another element that they can compose with to give 0 the identity back again. Okay, in addition, the composition law here actually obeys an additional property. It also obeys commutativity, which isn't an axiom of group theory. It isn't necessary for you to obey commutativity in order to be considered a group. But in this case it is true that a plus b is the same as b plus a, i.e. the composition law is symmetric down the diagonal line, okay, and therefore we would call the integers under addition a commutative or abelian group. Okay, right, so that's just a little bit of a reminder of the group of integers under addition. Now let's discuss the subgroups of the group of integers under addition. Okay, so the way I'm going to do this is I'm firstly just going to show you a whole bunch of subgroups of the integers under addition. And then what I'm going to do is prove that I've actually just shown you all of the subgroups of the integers under addition, that there are no more beyond this bunch that I've just shown you. Okay, so that's how we're going to go about this. So firstly, let me just chuck at you a bunch of subgroups of the integers, and then what we'll do is prove that they are actually subgroups of the integers. Okay, right, so the subgroups that we are going to look at initially are of the form A times Z, okay, where A is some non-negative integer basically. So A could be 0, it could be 1, it could be 2, it could be 3, it could be 4, it could be 5, and hopefully you're getting the idea there. A natural number or 0, because 0 isn't considered a natural number. Okay, right, so we're going to consider subgroups of the integers of this form. Now let me firstly tell you what this actually means, because I haven't defined what I meant by AZ like so. So what I actually mean is all integer multiples of A basically. Okay, so let me now write out in set theory notation what this actually means. AZ means the set containing all integer multiples of A. So basically A multiplied by any integer, little z here. So Z times A, and this is where you actually need to be aware of a bit of classical algebra at the moment. Okay, so I know we have not yet rigorously gone through multiplication on the integers. Okay, but I'm assuming that you are familiar with how to multiply integers together from your understanding of classical algebra. Okay, so just think of this in terms of classical algebra rather than in terms of abstract algebra at the moment. Okay, so you take all integer multiples of A, so you multiply A by every possible integer, so ZA, where Z is an element of the integers basically. Okay, so let's make this a little bit more obvious. What's this going to consist of then? Okay, well, when we go through and multiply by every single integer, we can start off with 0. Now, of course, we know that when we multiply 0 by A, we'll get 0 back again, so we'll automatically get the element 0 there. When we put in 1 here for Z, okay, we'll then get A, so 1 times A is A. When we put in negative 1 for Z here, we'll then get negative A. When we put in 2 for Z here, we'll get 2A, and so on. And you'll take all integral multiples of A, basically, all integer multiples of A. So you'll get 0A, negative A, 2A, negative 2A, 3A, negative 3A, 4A, negative 4A, etc., etc. Okay, so you get all integer multiples of A, basically. That's what I mean by AZ, basically. All integer multiples of this number A. Okay, right. So my claim is that these subsets here of the set of integers are actually subgroups. Now firstly, let me just explain to you that they are all going to be subsets. Okay, well that follows from the fact that I have limited what A can be. I've said that A has to be 0, 1, 2, 3, 4, 5. Now if A is any of these basically, you're always going to end up with a set of integers here, because whenever you multiply two integers together, you get another integer. So the answers that we're going to have here are always going to be integers. So we are going to get a subset of the set of integers here. So these sets here are always going to be subsets of the integers. And my claim is that they're actually going to be subgroups. So before we prove this for the arbitrary AZ, let's just do a few examples and get some intuition here. Okay, so let's start off with a nice simple example. Let's plug in A is equal to 0 here. So we're taking the set of all integer multiples of 0. Well, when you multiply 0 by any integer, you'll just get 0 back again. So actually, 0Z is just the set containing one element, which is the set containing 0, basically. Okay, and we know that that is actually a subgroup of the integers, okay, because this is just the identity element, and we know that in an arbitrary group, the subset just containing the identity element is always a subgroup. It's one of those trivial subgroups. So in fact, this does form a subgroup, albeit one of the trivial ones. Okay, so excellent, we've got a subgroup there. Now let's do 1 times z. So we're now letting a equal 1. Now this is the other trivial subgroup, because if a is equal to 1, then you're taking all integral multiples of 1, all integer multiples of 1. So you're going to just get the entire set of integers back again. So 1z is just the entire integers, and therefore that's the entire group. So the first two are just the 2 trivial subgroups, basically, that are always there in any group, and therefore are certainly subgroups of the integers. Okay, right, so there we have 2 subgroups of the integers, okay, the 2 trivial subgroups. Now let's go on to the more interesting ones, the proper subgroups. So let's go on to 2z, okay, so 2z now. Okay, right, so 2z is going to be all integer multiples of 2, so this will be the set 0, 2, negative 2, 4, negative 4, 6, negative 6, so all even numbers basically, all integer multiples of 2. Okay, all the multiples of 2. Right, okay, so let's just think through why this is going to be a subgroup then. It's certainly a subset of the integers. What we want to think through is why it's going to be a subgroup. And hopefully by going through the arguments for 2z, we will begin to understand why the arbitrary az is actually going to be a subgroup. Okay, so our arguments will generalize very nicely to the arbitrary az. Okay, so let's just go through the axioms of group theory then. We need to make sure that it is closed. Okay, we need to make sure that it obeys closure, basically. Okay, so what does that mean? We need to make sure that if you add any 2 elements of this set, 2z, that you end up with another element of 2z. So basically, we need to make sure that when you add 2 multiples of 2, 2 integer multiples of 2, together you get another integer multiple of 2. Well, hopefully that should be obvious. When you add 2 even numbers together, you end up with another even number. So hopefully that should be obvious to you that this is closed. Whenever you add any 2 elements together here, you're always going to end up with another one in here. We know we don't need to worry about the second axiom of group theory, associativity. We know that's always true whenever you look at a subset like this with this inherited composition law on it. Okay, we do have the identity element in our subset here, and we'll always have the identity element in any one of these subsets. Okay, so that's excellent. So we've got the identity element. Okay, and finally inverses, well hopefully that should be pretty obvious as well, because we've always got the negative elements for any element that you have. So for instance, 2 has its inverse here, negative 2, 4 has its inverse here, negative 4, 6 has its inverse here, negative 6, and of course negative 2 has its inverse, that's 2, negative 4 has its inverse, that's 4, negative 6 has its inverse, that's 6. So we've got these pairs of inverses basically always together, okay, because whenever you have a multiple of 2, its inverse is also a multiple of 2 basically. Okay, so we've got inverses in there as well, so that forms a nice subgroup then. Okay, so now let's try and extend that argument to the arbitrary az here. Okay, so let's now think of why az is going to be closed under addition basically. Okay, so what we want to say is that whenever I take 2 elements of this set, az, and add them together, I'll get another element of this set, az, basically. Okay, so if I take 2 arbitrary elements, the 2 arbitrary elements of this set will be of the form za plus, let's say, z prime a. Okay, I hope you understand why that is. Okay, what I'm saying here is all the elements of this set are integer multiples of a. So I'm going to let z and z prime be 2 arbitrary integers, okay, and now I've got 2 arbitrary elements of this set, Okay, if you want a concrete example, z here could be 1 and z prime here could be 2. Okay, these are just two arbitrary integers, and therefore these are two arbitrary elements of this set. Any element of this set can be written as an integer multiple of a, because that's the very definition of this set. Okay, so I'm just saying compose two arbitrary elements of this set together here, and now what I want to do is show that this is going to be another element of this set. Okay, well here's where we're going to use something that we haven't gone through rigorously in abstract algebra at all yet. Okay, but which I'm relying on you having an understanding of from classical algebra. Okay, and this is the distributive property. And really, to go through this rigorously, you need to go on to ring theory. Okay, but you will be familiar with this from classical algebra. So basically, what you can do is you can factor out the a here. So you can rewrite this as z plus z prime times a. So hopefully that should be familiar to you, even though we haven't been through it rigorously. Okay, and that's called the distributive law. Okay, that this is the same as this. Okay, right. Now what we can say is, okay, z and z prime are just integers. So when I combine them together, we'll get some new integer, which I could call z double prime, and therefore the answer to za plus z prime a is going to be z double prime a, where z double prime is an integer. Okay, i.e. the answer to what two integer multiples of a added together is always another integer multiple of a. So this is just a very abstract way of saying that when you add two integer multiples of a together, you get another integer multiple of a. And the reason that that works so beautifully is really that you can factor out the a here like so. It's because of the distributivity of multiplication over addition in the ring of integers, if you know what that means. Okay, if you don't know what that means, just use your understanding from classical algebra. Okay, right. So basically, when you add any two integer multiples of a together, you get another integer multiple of a. So this is closed under addition, basically. Okay, associativity we don't need to worry about. We know we don't need to worry about that. If this wasn't associative, then the group of integers under addition wouldn't be associative. Okay, so we can cross axiom number 2 off. The identity is absolutely always an element, because whatever a is equal to, when z is equal to 0 here, you'll get 0. So you've always got the identity element in there, so we can cross axiom number 3 off. Okay, and finally, inverses. Well, we know that we've always got the inverses present. The inverse pairs are always present. So if you've got, for instance, za, okay, so if you've got an arbitrary element, za, some integer multiple of a, you will also at some point have in the set negative za, and these two will be each other's inverses in that subset, basically. Okay, again, because when you add these two together, what you can do is factor out the a here, and you can say that this is z plus negative z, which I'll put in brackets like that, times a, basically. Okay, then you can just combine z and negative z together in the integers to get 0, and then you'll get the 0 times a, which is 0, basically. Okay, so that's why inverses will always be present within this subset az, basically. Okay, so all of that was just in order to prove that all of these subsets here of this form az, where we're taking all integer multiples of this number a, which is 0, 1, 2, 3, 4, 5, etc. And by the way, I should just explain why we haven't got the negative numbers in that list. Why would we not want to bother doing negative 1? You could do negative 1z, but you would get the same subset as for 1, basically. Equivalently, if you did negative 2z, you would get the same subset as for 2. If you did negative 3z, you would get the same subset as 3. So, because I didn't want degenerate examples, that's why I omitted the negative integers from that list. Okay, so for absolutely all of the a's in this list, you will get a different subset firstly, all of them give different subsets, and all of them give subgroups basically, as we've just gone through the arguments for why they obey the axioms of group theory. So that is a whole bunch of subgroups of the group of integers under addition. Okay, in the next video what we will do is we will prove that actually there are no other subgroups outside of this bunch of subgroups. All subgroups of the integers are of this form basically, az for some a is equal to 0, 1, 2, 3, 4, 5, etc. Okay, there are no subgroups that have a different form to that basically. Okay, and that's what we'll prove in the next video.